Chapter 10, Section 4, Gram-Schmidt process. The Gram-Schmidt process is a mathematical technique used to transform a set of linearly independent vectors into a set of orthogonal and normalized vectors. These orthogonal vectors span the same space as the original ones, making it easier to analyze and compute within the space. It converts a complicated representation of a vector space into one that is more intuitive and computationally friendly. The Gram-Schmidt process is important in data science because it simplifies complex vector spaces into orthogonal bases, which improve computational efficiency and numerical stability. It is foundational in algorithms like QR decomposition, which is widely used in regression analysis, dimensionality reduction, and solving systems of linear equations. By providing a clear geometric structure, it aids in better understanding and manipulation of high-dimensional data. Let's get intuitive understanding. The Gram-Schmidt process is a method to transform a set of linearly independent vectors into mutually orthogonal vectors. By further normalizing this orthogonal basis, we obtain a set of orthonormal vectors, which each vector has a length of 1. This process simplifies a set of vectors that were initially intertwined or difficult to handle into a more computationally and conceptually manageable form. For example, it creates a set of perpendicular axes in the space, similar to a coordinate system. The Gram-Schmidt process is somewhat complex, so let's start with a simple example. In the Gram-Schmidt process, a set of linearly independent vectors is initially given. Here, we have two vectors, v1 and v2, as an example. Since these two vectors are not mutually orthogonal, let's transform them into orthogonal vectors using the Gram-Schmidt process. The first vector, v1, is used as it is, and it becomes the first orthogonal basis vector, u1. The second vector, v2, is projected onto the direction of the previously created orthogonal vector, u1. Here, the inner product of v2 and u1 equals 1, and that of u1 and u1 equals 2. So the projection can be expressed in this way. Next, subtract the projection component to obtain u2. So, why is the projection component subtracted? When v2 is projected onto the direction of u1, the component in the same direction as u1 is obtained. Subtracting this projection component from v2 removes the part aligned with u1. As a result, the remaining component is orthogonal to u1. This ensures that the new vector u2 is orthogonal to u1. To make the length of each orthogonal vector equal to 1, the next step applies normalization. By normalizing u1 and u2, we can obtain an orthonormal basis. This step is optional, but by applying this formula, each orthogonal vector becomes a unit vector while preserving direction, making it easier to work with. Let's apply this formula to u1 and u2. Then we can obtain normalized vectors u1 hat and u2 hat. These vectors now form an orthonormal basis. They are mutually orthogonal and have a length of 1. Now, let's see the general description of the Gram-Schmidt process. Given a set of linearly independent vectors vi in Rm, the Gram-Schmidt process constructs an orthogonal set of vectors ui as follows. As the first step, start with the first vector. Set u1 equals v1. Second, iteratively compute orthogonal vectors. For each subsequent vector, vk, subtract the projection of vk onto each of the previously computed orthogonal vectors, u1, u2, uk minus 1. Third, normalize to form an orthonormal set. If orthonormal set is desired, normalize each orthogonal vector uk by dividing it by its norm. The resulting set will be an orthonormal basis. Let's wrap up. The Gram-Schmidt process transforms the space spanned by the given vectors as follows. The first vector is used to define the first orthogonal direction. The second vector is projected onto the direction of the first vector, and its projection is subtracted to create an orthogonal direction. This process is repeated so that all vectors are adjusted to become mutually orthogonal. The space spanned by the original vectors and the space spanned by the orthogonalized basis are the same. Using an orthogonal basis makes operations such as projections and inner product calculations more efficient. And it becomes easier to understand the relationship between vectors. Thank you for watching. Please thumbs up and subscribe to my channel.